Hello, how you doing? It's Mike here, and in this video we're going to talk about why my horrible handwriting says hyperbolic functions, why they are called hyperbolic functions. Why do we call hyperbolic functions hyperbolic functions? What's the rationale? So first of all, I want us to go back to our pre-calculus days where we talked about parameters, parametric equations. So we represent a variable x in terms of cosine, a variable y in terms of sine. So we said x was equal to cosine of some value t, so x was equal to cosine of some value t, and y was equal to some value of t. And this was provided that 0 is less than or equal to t, which was less than or equal to 2 pi. And what this gave us is this gave us the unit circle. So this gave us the unit circle. I'm going to do my, actually I might just cheat. So there we go. So I got a unit circle in here. Bam. So we got a unit circle here. So notice, let's do this in red so we can see it. So there's going to be a radius here. There's going to be a radius. And this point right there is going to be cosine of t, comma, sine of t. So that's going to be cosine of t, comma, sine of t. And this will give us an area. This portion here gives us an area that exists between the x-axis and that point. So the unit circle has a special relationship because we know that x squared plus y squared will always equal to a value of 1. So this radius that exists will always, will always be a value of 1 because we're able to prove that x squared plus y squared is always equal to a value of 1. So this is a little bit different. So now let's go ahead and talk about what happens if we have our hyperbolic functions. So I think it's always important to talk about that similarity of our hyperbolic functions. So here in our prior video, we discussed the relationship of hyperbolic sine and hyperbolic cosine. So let's go ahead and graph hyperbolic cosine of t, and then we're going to let y equal to hyperbolic sine of t. And what this looks like, this is a little different. It's a little different, so we're going to have, I'll do it in red so we can see it. Oh, this is going to be tough. So we're going to come down here. Well, actually it wasn't so bad. So we got our curve here. Let's see if I can try to be as symmetric as possible. It's actually not horrible. You can tell I practiced this once or twice for this video. So well, it's not the best, but it's not horrible. So well, it's not the best, but it's not horrible. So now if we pick a point, I was going to pick a point here. This will be the point cosh of t, comma, sinh of t. So that'll be this point cosh and sinh. So notice if I connect from the origin to that point, then I will create an area here, and this area is what is key, the part that I'm shading in blue. This area is very important to us because there's a relationship that develops from this area. So there's an area that develops from, there's a relationship that develops from this area. So let's go ahead now and talk about, this parameter in terms of sinh and cosh. So if 0 is less than or equal to the value of t, which is less than or equal to a value of 2 pi, the parameter t can be interpreted as the angle in the unit circle. So going back up here, if we look at this, we could actually see that this creates an angle. So that angle will exist between the x-axis and that value. But there's going to be a similar analogy for our parametric hyperbolic functions. So if we see here, if that x is a value, if x is equal to cosh of t, and we know x is equal to cosh of t, we recognize that t is always going to be greater than 0. So we see that t is always going to be greater than 0, and it's greater than 0 on this right side. So when t is greater than 0, it's going to be on this right side. And the interesting thing about this is that this curve, so I'm just going to highlight it in yellow, so this curve right here. So when t is greater than 0, we have this curve right there. So I try my best to outline it in bright yellow so you can't miss it. So if x equals cosine of t, hyperbolic cosine of t, and this is going to be greater than 0, which is going to be greater than, actually, I didn't mean t greater than 0, I meant cosh of t is going to be greater than 0 because that's our x parameter. So this will be cosh, which will be greater than 0 because that's going to be our x parameter. So if this is greater than 0, the curve which we've shown right here, so this curve right here, is going to have a very unique relationship with this part that we shaded in with blue. So the curve to the right, I'm sorry, to the left will have a very unique relationship. And that unique relationship is that this is going to be the unit hyperbola. The unit hyperbola. And that's the reason why we call this section hyperbolic functions. So the right half of the larger curve, so the right half of this larger curve is going to be the unit hyperbola. And it can be shown, and I don't really know if we can prove it, but it can be shown that if t is greater than or equal to 0, then the parameter t, just like we talked about this for our unit circle, then the parameter t can be interpreted as twice this blue shaded region. So twice now this blue and white shaded region, as twice the blue shaded region. So before, this horrible region, so before we were able to look at that parameter as the angle theta. So in terms of our non-hyperbolic functions, the parameter t could be related as the angle that exists between the x-axis and that value of t along the unit circle. And here the parameter can actually distinguish and give us twice the area of that blue shaded region, which I think is a very unique circumstance. But that's the reason why we call these hyperbolic functions, is because of the representation in relationship to the unit hyperbola.